Okay, good afternoon. Everyone, can you hear me? Okay, thank you. So just a quick reminder. So the first programming assignment is due tomorrow. So make sure you submit your report and the code on time. Okay. So for today's lecture, we'll talk about deep learning model efficiency, which is a very important aspect for a lot of real world application, and certainly for medical imaging as well. So we witnessed huge involvement with the deep learning architectures, right? So from the beginning of the AlexNet, there's a lot of improvement in terms neural network architecture. So a lot of them going very deep, right? So you have the ResNet can go like 150 layers, and even now you can design neural network architecture, thousands of layers. But although they improve the performance, but in company, the computation also increased a lot. Okay, so if you look at this figure here, it shows the progress of the neural architectures in the recent years. And also in the vertical, you can see how many computation is also increased. And this is also a table just show a very detailed comparison, right, with different neural network architectures and what is their compute operations in terms of multiplication and addition. So here, if you look at the AlexNet, compare with AlexNet and VGG, right, the total number of parameters, right, in a network almost doubled, right, double the parameter size. And also the compute also increased significantly, right? So this will incur a large memory and a computational cost. But a lot of real world applications, it's not like we have a data center. We have a dedicated computing cluster to, enable to allow these kind of large model to deploy, to train, and to do the inference. A lot of cases we have the edge devices that with limited computing resource, right? For example, your smartphone, iPad, right? The smart cameras, right? The surveillance cameras, they want to do some object detection, traffic accident detection, right? Also the drones, right? They were limited by the computing, also limited by the the power resource they have, especially the drone, right? If you want to deploy a computer vision algorithm on the drone, then you have to be aware of the power consumption. And for the medical image computing, it is the same, right? So medical image usually have a large volume, right? We have those 3D scans, and it's a lot of data. If we deploy a huge model, then the computation will be significant and also will incur a lot of latency. For example, if a large model and you want to do the segmentation, it can take minutes to finish, to segment the entire, the volume of the CT or MRI scans. So we want to come up some ways or solutions to address that, right? We want to have these kind of computation or memory efficient network designs so that can be deployed on some of the resource limited platforms like mobile phones. There are several ways to achieve efficient neural networks. So here are four very popular ways to achieve these efficient networks. So the first one is the efficient network architectures, right? So we talk a little bit about this when we discuss give the introduction of deep neural networks. So there are some networks or special operations has been designed to considering the computation efficiency for the network architecture. For example, the mobile nets. So it is specifically designed for mobile applications, right? Those depth separable convolution and pointwise convolution to achieve these computation and memory efficiency. So that's more on the architecture design, right? You want to come up with new operations that can have much better computation efficiency. And the second category is the network pruning. Okay, so the basic idea is that if you have this large network, maybe it's over parameterized, right? Do you really need these many parameters to achieve this certain level of performance? Maybe some of the network or neurons will be redundant, right? They learn something similar. So we don't necessarily need to have these many parameters. We can do some pruning, right? Basically reduce the number of parameters in the network, but at the same time, the goal is trying to maintain the performance, right? You reduce the model size, but at the same time to maintain the same level of performance or very similar performance. And the third category we can do is to do some quantization, right? So usually the network is doing computing in this full precision, right? That's the 32-bit floating point operations. But for some of the hardwares, maybe it's not able to accommodate the full precision. Also, if you want to reduce the computation, and if you reduce the bit width, right, instead of using the 32-bit floating point, you can reduce to maybe 8-bit or 4-bit. And to the extreme case, you can go with the binary case, right? Just 1 bit, okay, for the network parameters as well as the activation. So that will reduce a lot of computation. So this is especially useful, when we talk about tiny machine learning, right? So if we want to deploy a network, say on not even mobile phones, you want to deploy something on extremely resource limited microcontroller, right? So for example, you want to deploy some network on maybe, let's say, a light switch, something like that, intelligent light switch, right? So you, based on the cost effectiveness, right? So you wouldn't have very large or powerful chip embedded in those devices. So more likely a very cheap microcontroller. So how can you deploy a network that is able to fit on that extremely resource limited device? Quantization is a very effective way to achieve that. And another one is the knowledge distillation. Okay, so the basic idea is that you have a teacher network, which can be a very large model. Okay, and you also have a student network, and usually it's a much smaller network. And the student network is considered the target network. Okay, we want to teach a very good student so that it has the capability to match the performance of the teacher. So in this case, we can just deploy the student network on those resource limited device, right? So because it have very small or lightweight network architecture. So that's the knowledge distillation. So which is very intuitive, right? You want to distill the knowledge from the teacher to the student, so the student can achieve the similar performance, but with the benefit of being lightweight or computation efficient. So let's just look at the each of the individual category and how different architectures of different strategies can achieve these computation or memory efficiency. So let's look at the efficient network architecture designs, right? So MobileNet is a very famous architecture. A lot of mobile applications adopt MobileNet. So there's actually right now 3 versions for this MobileNet family. So MobileNet V1, V2, and V3. So each of the generation, they do some improvement in terms of performance as well as the efficiency. So the most innovative component for the MobileNet is propose this having this steps-wise convolution and also point-wise convolution to reduce the computation as compared to the traditional convolutional operation. And the second network is the ShuffleNet. So it has the use the method called group convolution. So for the traditional convolution, right? So we have a filter, right? So we're gonna operate on all the channels of the input feature map, right? Say if at n channels, then your filter or the kernel also have the channel dimension of n, right? 3 by 3 by n. So that's the typical filter or kernel size of the traditional convolution operation. So in the group convolution, the idea is that want to divide these channels into several groups. For example, let's say we want to divide these n channels into 3 groups, right? So each group have an equal number of channels. So divide them into 3 groups. At the same time, if you want to use m filters or m kernels, you also divide them into the same number of groups. Okay, here the example is 3 groups. Then you do this convolution in a group fashion, right? So the first input group, the group in the input feature map, then you just consider these n/3 channels, right? And you also consider the filter will have this n by n by n/g. G is the group, here is 3, right? You do this kind of convolution, and here each filter will operate individually on each of the channel. So you generate the n by 3 feature maps, right? So just like the depth-wise separate convolution. So each filter will operate on the each of the channel and generate a feature map. So in this case, the number of operations can also be reduced. So here is an illustration, graphic illustration, how this group convolution works, right? You divide the total channel into a certain number of groups, and you do the convolution based on the group. Okay, so these red or pink and the green and the light blue indicating 3 different groups. But if we do this kind of group convolution, there is a potential side effect, right? As you can see that, all within these group, right, it's never get to see the information from other groups, right? So each of the, the color indicating the information flow is gonna just within these group, right? There's no information exchange, between different groups, right? But here, it's not the ideal case, right? So we wanna, encourage some of the information flow from different channels, so you can learn some of the information, do some collaborative learning. So to address this issue, this ShuffleNet introduced this notion of shuffle the channels, right? So once you do the group convolution here, you get the feature, right? So basically have all these, the same number of the channels at your input here, and you want to try to mix up the channels within different groups. Okay, so you can shuffle the channels. So when they go to the next group convolution, right? If you look at the last column here, the last figure here, within this red group, right? You also have some of the channels from the green and the light blue ones, right? So there is some information exchange between the other groups. So this will help the model learning. And the third network architecture is called GhostNet. Okay, so their motivation is by observing the feature maps, right? So they visualize some of the feature maps from the first group, residual group in ResNet 50. And they observe some of the feature maps actually very similar to the others, right? So for example, they're using this bounding box with the same color, right? So if you look at this feature map, the red one and this one, they are very, they look very similar, right? Except maybe there's some, color difference or gray level difference, right? Basically, you can, reduce the gray level, from this feature map to obtain this one. And similarly here, right? So if you look at the green one, somehow they are also very similar. but not just like this one and this feature map. They look very different, right? But here, these two, they are very close to each other. Also for this blue pair here. So then based on this observation, then the question here they want to answer is it possible, to have some cheap operations? If let's say I just have this feature map, is it possible we can have some cheap operations to get another feature map like this, right? Instead of using the usual kernel convolution to generate this feature map, I can derive this feature map from here, right? Using some cheap, operations, like maybe affine transformation, or maybe just, some of the histogram, maybe adding some noise or make the histogram differently to make this feature map. So that's their basic observation and motivate their proposed method. And the idea, so this figure shows their idea, right? So you have the input, and you can using reduced number of kernels to generate a feature map like this, right? So then you can using the so-called ghost module, right? So here is some transformation, right? To transform each of these feature map or channel into a new one, right? So this is, as compared to the classic convolution, this is gonna be a much cheaper operation, phi, to generate additional, feature map, right? So here, if you look at here, this is the input, right? You can do the identity mapping. You have this number of feature map, but based on these transformations, you can generate or double the size of the channels, right? So in this way, they are able to reduce the computation, but maybe maintain the same diversity of the feature map. So that translate to the similar capacity for the feature representation. And this figure shows a comparison with the GhostNet, as all the previously efficient network architectures, right? So they have the ShuffleNet v2, MobileNet v2, and v3. And the red line is the GhostNet, right? So here on the horizontal is the floating point operations, right, in the millions. So typically this is the metric to compute, to estimate the total compute of the network, how many floating point operation is there for a particular network. So if you look at, if they have the similar compute, right, for different network, they were able to achieve better performance, right? So this red line across the spectrum of the flops, right? So they consistently outperform the other network, okay? So you can also say, if I set the threshold of 75% accuracy, that's my threshold, right? So if you look at horizontally, right, to achieve 75% accuracy, and GhostNet require less compute, right? You look at the vertical line here, right? So the MobileNet v3 require more compute to achieve the same accuracy. Okay, so that's some of the classic, efficient architectures, particularly designed for CNN. Okay, before we continue, any questions for this efficient architectures? Okay, so then we go to the next category, that is network pruning. Okay, like I mentioned before, right? So the idea is just to remove some of the weights which may not have enough information, or maybe they are redundant to others, right? So how to remove the neurons or weights is considered like a score, right? You can design some of the scores to help you to decide, right, which weights or neurons you want to remove from the network. The simple one is just to look at the magnitude of the weights, right? If the magnitude of the weights is very small, close to zero, then pretty much it does not contribute too much, right, in terms of the optimization. So we can remove that. And once we remove those neurons, right, we generate like this sparse network as compared to the original one, right? Obviously, there may be, because the connections are kind of destroyed, right? So this is become sparse connections for the network. To kind of regain the performance of the network, so typically we have to retrain the network again, okay? So basically you have the, train the network, right? Maybe it's a ResNet, let's say 50, right? Trained on ImageNet. And you do this pruning, right? To remove maybe 30% of the weights or parameters of the network, right? Just to reduce the size. Once you do the pruning, you have to retrain the pruned network to maintain the accuracy, okay? So you can do this in one shot, or you can do this, iteratively, right? Rather than, pruning 30% at one time, maybe you can, do this pruning incrementally, right? Each iteration you prune maybe 5%, right? You gradually prune the network until you reach that, 30% threshold or bar you set, okay? And for the network pruning category, there's actually two general approach. And one is the unstructured pruning. So basically just we discuss here. So we prune individual parameters, okay? So kind of we prune each of the individual weights in this weight matrix, okay? So in this case, we can end up with some of the network is kind of irregular, right? So each layer we may have, in this weight matrix can be distributed anywhere, right? The preserved weights or neurons can be anywhere. Okay, so this will cause some of the challenges for hardware implementation, right? So some of the hardware implementations or some of the deep neural network libraries, they are not friendly to these kind of libraries or hardware. They cannot leverage some of the optimization for speed. So so then people have come up the other category, so that is called structured pruning, right? Instead of pruning individual weights, the structured pruning will just remove the entire filters or channels. This will kind of give, considering these kind of hardware or software optimized for dense computation, okay? And this table shows, just give an example, how the pruning performance looks like. Okay, so actually taking from this paper, learning efficient convolutional through network slimming. So basically they are doing structured pruning, right? So instead of removing individual weights, they try to remove channel as a unit, right? Remove the entire channel instead of like one weights from this feature map, feature channel, okay. And this is the result on Safari 10 and the Safari 100. So let's look at the what's their performance, right? So they're using VGGNet as the baseline. Okay, so this is the original VGG network. Okay, and they have 20 millions of parameter. Okay, and has these many of computation in terms of flops. Okay, and this VGG network achieved 6.34 test error on Safari 10. Okay. And when they're using this channel network slimming method to prune the network, they prune the network, 70% pruned, right? You can see they reduce the number of parameters to only 2.3 million, right? As compared to the original, you have 20 millions. And also they were able to reduce the computation by half, right? So from 7.97 to 3.91, okay. But if you look at the test error, right? So the error actually also reduced, right? This is a good thing, right? You reduce the model size, compute, you also achieve a gain on the accuracy, right? Remember, this is the test error, right? The small, the better, right? So they are able to improve the test error. So one thing could be because of the smaller network, right? Maybe you have less chance to be overfitting, right? The model is able to generalize well. So you will see a small, performance improvement, okay? So they also do this DenseNet and the ResNet, right? So they have different pruning ratios they tried. And so, more pruning will result in, a smaller network in the parameter and also compute, right? But if you prune more, obviously, you may, have some of the, some of the performance degradation. But in this case, it seems like they are also able to have better test error. But if you continue to prune, maybe 90% pruned, you may see the test error is gonna increase, right? Because you improve the model too much, and it just the network representation capacity is just not enough because of the smaller network. Okay, so these are some of the performance comparison, using different network baselines and also pruning at the different pruning ratios. Okay. And the next category is the network quantization. Okay, so the quantization for the network is the process, you approximate the network that's using floating point by the network of low bit width numbers, like I mentioned, right? So typically the network operates in the full precision, 32-bit floating point. And we want to maybe use a low bit width numbers, right, for the weights as well as the activation map or feature map, right, maybe 4-bit or 8-bit, okay. So the quantization will dramatically reduce the memory requirement and the computational cost, right, because you are using low bit to represent the model, right. That requires less memory and also less computation. And the goal of the quantization is that we want to reduce the, the bit width of the network, right? But at the same time, we want to minimize the impact of the performance degradation, right? Obviously, if you reduce the precision, right, so the performance will drop. But the goal is that can we come up with a solution? So you quantize the network, but at the same time, you are still able to maintain, similar level of performance. So the quantization method can be, roughly divided into two categories. So one is quantization aware training. So that means you consider quantization in the training stage. Okay, so that's quantization aware training. And the second category is the post-training quantization. So basically you already trained the model, then you just do some quantization on the model before you actually do the, deploy the model on maybe some of the edge device, okay? So for the quantization aware training, the QAT, and the model is quantized and fine-tuned using the training data to adjust parameters and to recover the accuracy degradation, right? So you have a model and you do the quantization, right? You also have access to the training data. Because of the quantization, right, you suffer from some information loss. So this will, affect the model performance. So you want to, kind of fine tuning or retrain your model to try to regain that information loss, right? So you do this kind of quantization aware training. Hopefully after this kind of retraining or fine tuning, the model the performance will not drop significantly. So this is the illustration of the quantization aware training procedure, right? So you have this weight and you go through this quantizer, right? So depending on the bit width you want, so you will kind of quantize to the corresponding bit width. And then you do the back propagation, do the update, right? So this is involved in the training process. And for the post training quantization, right? Basically, there's no retraining or fine tuning, right? So you have this pre-trained model, and you have maybe a small set of calibration data, and you want to calibrate, right, how much quantization you need for each of the layer, right, to meet your goal, right? Let's say I only have this many of memory or computation budget, then you want to calibrate on how much level quantization you want for this pre-trained model, okay? So the benefit of these post-training quantization is that it's much simpler than the quantization aware training, right? Because you just do some quantization calibration, right? How much you want to, what's the range or scales you want to do the quantization. So there is no fine tuning or retraining involved. But the disadvantage or limitation as compared to the quantization aware training is that the performance usually, suffer more, drop as compared to the quantization aware training, because this QAT considering these quantization error or performance drop during the training stage, right? During the fine tuning and the retraining, trying to recover that kind of performance drop. So for the quantization of the network, if we have the lower precision, it also provides the benefit of better energy efficiency, right? So here is a figure doing the comparison of the energy cost for different precisions on the 545 nanometer technology, right? So here is the 8-bit addition, 6-bit addition, 32-bit addition. Okay, so there's also multiplication. So you can see how many energy consumption, associated with each of the operation, right? Obviously, if you have low bit width or low precision network, and the energy consumption can be very small, okay? So this is very important for some of the like a tiny machine learning applications, right? Maybe some of the devices you have to operate 24/7, right? It's constantly running, right? You don't want have a device or network deployed on that device, consume too much of the energy, right? Then it's not very cost effective. So the quantization can also provide this kind of benefit to achieve energy efficiency. Okay, so any questions about quantization? Okay, so the next category is the knowledge distillation to achieve efficiency, network efficiency. So the knowledge distillation, or KD, is basically a process, right, to transfer some of the knowledge from a large model to a lightweight, easier to deploy single model without significant loss in performance. Okay, so here for the large network is going to be the teacher, right? So in many of the cases, you don't have to limit to just one or single teacher. So actually you can use in multiple large networks as multiple teachers, and using this a committee of teachers to teach a lightweight, easy to deploy student network, so that the student network can learn better. Okay. So since this is terminology called knowledge distillation, right? So we care about what kind of knowledge to transfer, right, from the teacher model to student model, right? So the teacher model usually is very large, right? So here, in this kind of network, you can see it has more layers, right? More neurons in each of the layer. But for the student network, typically it's very small, by considering the capacity of the on the target device, right? How many memories, how many compute you have on the target device, you can specify, how large is the student model. And then the goal is trying to distill the knowledge or transfer the knowledge from the teacher model to the student model, okay? So there are a few ways, we can kind of transfer different knowledge from the teacher network to the student network, okay? So the first one is the response-based knowledge distillation, okay? So this is, you also typically see this is like a logic-based knowledge distillation. So here, this graph shows like how this response or logic-based knowledge distillation work, right? So let's say you're doing image classification, right? So you have a teacher network, you'll have a smaller student network. So they have different architectures. And the logics will be the last, the softmax prediction, right? Those probabilities, right? Which based on that, we can determine the category this particular input data belongs to. Okay, so the knowledge distillation is based on these output logic. Okay, so let's look at the bottom figure here. Just give you more details how this works, right? So you have the teacher-student network, and you have this you have the training data. So the teacher network will generate a prediction, right? So we call this soft logics or soft targets, right? The hard targets is considered the ground truth, like the one-hot encoding, right? So you only have one place that has a probability of 1, right? That's the ground truth. But in the soft target come from softmax is that, likely all the categories will have some value, right? Certain probability, right? Then we find out which one has the max value and take that as your classification. So in the logic distillation process, the student network will using the soft target output or soft logic output by the teacher and consider this as a ground truth, okay? And trying to mimic the prediction of the teacher network, okay? So there's a loss function, right? So the student network output and the teacher network output, right? The student is trying to come up with a prediction as close as possible to the teacher network, because the teacher network has a much stronger capability, right? The prediction is more accurate than the student network. Okay, so one typical loss function to use is called these KL divergence loss. So this KL divergence loss is basically measure the closeness or similarity between these two distributions, right? How different or how close this one distribution as compared to the other. Okay, so you can consider the teacher output, the distribution is the ground truth, right? So we can using the KL divergence trying to enforce the student network prediction, the distribution as close as possible to the teachers. Okay. So that's the response or logic-based knowledge distillation. And we can also consider feature-based knowledge distillation, right? So here in this figure, we show in the upper stream, we have the teacher network, right? So if you look at, each of the layer, teacher network has more channels, right? Have more channels means more parameters to, indicating the teacher network has a larger capacity. But for the student network, it's a smaller network. Okay, so in this feature-based KD is the student network trying to match the feature representation to the teacher network. Okay, you see for each of the layer, right? We have the feature FT is the feature from the teacher network. We also have the feature FS from the student network, right? So we can have a loss function here. Maybe we can measure the closeness of these two features and compute a loss, right? Obviously, there's a mismatch of the shape because these may be a larger feature map, more channels. This is smaller feature map, less number of channels. We can have some operation, maybe one-by-one convolution to have them into the same shape. Then we can do the matching, right? So the idea is that we want the student network have a very similar feature representation as the teacher network. So if we do this for all the layers, or maybe we selectively choose some of the layer, maybe high level representations, then if you have the similar feature representation, then you will likely output similar logics, right? So you will have achieve similar prediction. So that's the idea, right? Trying to mimic the feature representation of the teacher network. Okay, so that's feature-based knowledge distillation. So I take one of the table from this survey paper. So they kind of have a very comprehensive comparison of different KD method and what is the performance look like, right? If we don't do the KD, what's the performance of the smaller student network? And if we do the KD, how much gain we can achieve for the student network? Okay, so let's look at this column here, right? So they're using, this is the teacher network, okay? So let's just look at the first one, right? So the teacher network is ResNet 26, okay? So this teacher network achieved a 91.91% accuracy on Cepheid 10 data set, okay? Let's say we have a smaller network, ResNet 8, right? Obviously you have, much shallower, right? Here we have 26 layers, you have 8 layers, right? So much reduced model size. And it is obvious that, the smaller network, if we directly train it on the Cepheid 10, and this is the accuracy, right? 87.91. So about 4%, exactly 4%, drop, right? Or difference as compared to the larger teacher network, okay? So if they do the knowledge distillation, right, for the student network, as you can see that they were able to improve the performance by 0.79%. So that's the gain they can achieve by doing the KD. Obviously, they are still using the student network, but it's just do some knowledge distillation, then the student network is able to improve the accuracy by around 1 point, right? Then you can just deploy this student network on the desired hardware and do the inference. So here, the other rows shows different teachers, different student networks being used, right? These are the gains, right? On the parentheses, these are the gains they achieve by doing the KD. Okay, so for example here, right, this one, the teacher network is RedNet 152, and the student network is MobileNet V2, right, much smaller one, deployed on the mobile device. So if we do this KD, right, so they were able to achieve almost 3-point, improvement. So that's a lot, on this kind of smaller network, right? So this is a very effective way to gain performance, but you have the benefit of deploy a much lightweight or smaller network. So let's look at one case on knowledge distillation for medical imaging. Of course, there's a lot of cases, in the medical imaging, people using efficient architectures to perform various tasks, right? You can using these kind of MobileNet architecture for UNet to do segmentation. You can also using some other architectures for maybe classification, medical image classification tasks as well. So we'll not talk about those examples because they are very obvious, right? You just adopt the efficient architecture for medical imaging. So here for this knowledge distillation, they trying to come up with efficient medical image segmentation, right? So for this example, they were doing liver segmentation, right? So on the left, that's the ground truth. On the right is the student network. So basically a smaller network. This is without knowledge distillation, basically just train the smaller network on the data set you have, and this is the liver segmentation outcome, right? So as compared to the ground truth, right, these are some segmentation, right? So this one here and here. But if they're using the knowledge distillation, right, using a larger network as the teacher and do the knowledge distillation, and as you can see that their student with KD is able to improve the segmentation performance, right? These missegmentation is gone, right, for the student plus KD approach. And this figure shows the kind of the framework, how they do the knowledge distillation. So basically they are trying to go through this teacher network, the same input, and also go to the student network, a smaller one. And they trying to do some distillation of the prediction map, right? So this is like before you come up with the mask, right? You have the heat map indicating one particular class. So here they are distilled from the prediction map perspective. They're trying to match the student prediction map to the teacher prediction map. So the network can gain a better generalization for better performance. And this is the result they achieve. So they're using different teachers, right? So the T1 indicating RAUNet for the teacher. T2 is using PSPNet as the teacher network. T3 UNet++ as the teacher network. Okay, and they did for the liver and the kidney tumor segmentation. So these are the two different data sets. So this is the performance, segmentation performance for the teacher network. Okay, and then they want to, try different student network and see how their performance, right? So in the first row, the student network is ENet, right? If you look at the parameter count, right? So the teacher network, they are like 46 millions of parameter, right? But if you look at the student network, right? So this is the ENet, you only have 0.35 millions of parameter, right? This MobileNet V2 as the student network has 2.2 millions of parameter, right? ResNet 18 has 11.2 millions of parameter. So it's much smaller as compared to the teacher network, right? Especially for this ENet, okay? So this is the performance for the ENet, right? Just the student network without KD. This is the segmentation performance. Right, so if you compare, right, if you just compare the T1, the first teacher network, there's a significant gap, right, in terms of the segmentation performance from 0.685 to only 0.574, right, the DICE score, right? So there's a significant gap because of the model capacity, right, from 22 million to only 0.35 million. But if they do this knowledge distillation, right, using the T1 as a teacher and do this knowledge distillation based on this prediction map matching, right, they are able to significantly improve the student network performance, right? If you look at this bold-faced one. So they from 0.57 to 0.65, right? Here, if you compare with the teacher, it only have 0.033 performance drop, right, in the liver tumor DICE, right, which is a very small drop as if you compare with the original student and the teacher. So this is a very effective way to gain, to regain the performance for the student network. Okay, so they also do other, student networks. They achieve different levels of gains by using different teacher networks. Okay. So as I mentioned before, right, so you're not just limited to one teacher, so you can actually using multiple teachers. Maybe if you're interested in doing some KD, right, in your task or maybe your project, you can actually consider multiple teachers, right? And using multiple teachers, their output, maybe the average of their output as your final teacher to guide the student network. So that's usually will give maybe more performance improvement for the student network. Okay, any questions? Okay, so we've talked about all these different strategies that you can achieve, resource efficient or model efficiency for deep learning, right? But the question here is that, a single model will be optimal for a lot of, applications, right? So let's say you are able to train a very good smaller network, right? But is this sufficient for some of the real world applications, right? Because a lot of cases, the resource can be dynamic, right? Let's just take a drone, for example, right? The resource is depending on the power, right? So you have a full battery, maybe you have the bandwidth to accommodate a large model, right? But when the battery is low, then you can only accommodate a very small model, right? I mean, you can deploy a small model, just a smaller model in the beginning, right? No matter the power level or the battery level. But if you consider, I have full battery, but you still deploy a very small, a tiny model on the device, then the performance may not be optimal, right? So I think the better solution is, can we come up with a dynamic networks can adjust the trade-off between accuracy and efficiency, right? Let's say when the drone is at full battery, right? Maybe we can using a large network, right, to achieve very good accuracy. So when the battery level goes down, the network can adaptively change the structure somehow to reduce the the model size or the computation cost to accommodate or to fit the budget, right, on the drone. So that's one very interesting research area that is developing this kind of dynamic network, right? So for this kind of dynamic trade-off between accuracy and efficiency, one possible solution is you can install maybe multiple model variants, right, with various resource accuracy trade-off. For example, I can deploy maybe 3 or even more models on the drone, right? Let's say my drone is going to be equipped with ResNet 50, MobileNet V1, and a MobileNet V2. So I deploy 3 different models on my drone, right? If the battery, is at the full capacity, right, then maybe I can using ResNet because, it will give the best performance, right? Although it has the largest model in terms of parameters and the compute, right? 41 gig flops. So once the battery going down or the resource become very limited, then I can switch the model, right? I don't using ResNet 50 anymore. I switch to MobileNet, right? It has a better, efficiency, right? Only have 4.2 million parameters and only have 569 millions of flops, right? The computation reduced a lot. So it won't draw a significant amount of power on the drone device. Even if the power even goes down, then we can switch to MobileNet V2, right? Has even less compute. So you can deploy these multiple models and kind of switch between them according to the resource at the particular moment, right? So for the pruning, we can do the same, right? We can prune the model at different pruning ratios. For example, here we are using different architectures, right? Have different levels of model complexity. Let's say you just want to deploy a single model, right? We can prune the ResNet 50, the full model, at different pruning ratio, maybe 80%, 90%, 60%, right? So 6% definitely has the smallest, compute, but the performance might be the lowest, right? So maybe we can deploy these, 100%, 80%, and 60% model of the ResNet on the drone to achieve this kind of accuracy and efficiency trade-off. Okay, but one limitation of this solution is that it's not very scalable, right? So let's just say I need a very fine-grained level of a trade-off, right? This is more like has a very discrete or large interval, right? But I need a more refined trade-off, right? So you cannot deploy like 100 or maybe 1,000 models on the drone to switch between these 100 or 1,000 models, right? It's just not very scalable for a large AI system. And second of all, because you deploy multiple models, right, on the same device, there's more storage consumption, right? Instead of just store one model, here you have to store, 3 or even more models. So that creates some burden for the storage. And also for the memory, because you have to load, when you do the inference, you have to load the model parameters to the memory, right? So you can switch between them. So those are some of the limitations for this, simple solution. And there's some other ways to address this. I'm trying to come up just a single model and to achieve this kind of dynamic trade-off, okay? So for this paper, this resolution adaptive network for efficient inference, they are specifically, targeting the input. That is it really necessary to have a high resolution or larger resolution input to achieve better performance, right? If we can reduce the input resolution, then the computation can also be reduced, right? It's just like the similar effect. You reduce the network size, right? If your input is small, then the number of computation can also be, much smaller. So, and one observation is that if you have an easy sample, right? For example, this owl, is actually occupy a large portion in this image, right? If I do image classification, then the features of this object is very prominent, right? Even at a very small resolution, right? So let's consider this is the original resolution. And if I reduce or downsample this image to a smaller resolution, and the network may still recognize with high confidence this is owl, okay? Also, at the same time, do we really need a large network to recognize this easy sample, right? Maybe I only have a smaller network, maybe less number of layers, is already confident enough to make a prediction this is owl, because it's very easy, right? The features, everything is very prominent in the figure. But for some of the harder examples, right? For example, this owl here, because this image is taken from a long distance, right? This owl image is just occupy a small region, right? If you look at this original resolution, right? The owl is just very tiny region in this image. And if you reduce the resolution further, then this important region or the salient region become even smaller, right? And the network may not able to correctly predict this is our image because of the limited information. So this is considered a hard example, right? So we cannot using a smaller resolution or using a smaller network in order to achieve a very confident prediction. So in this case, we might have to using an original resolution and using a larger network so that the prediction can be accurate. So to achieve this kind of dynamic trade-off, right? So they design this kind of resolution adaptive networks. So the input are first, route to this lightest architecture. You can consider, this is like the smallest architecture, right? You only have maybe 2 convolutions, and using the smallest resolution and see how confident is the network prediction by just using the small resolution and a few layers of network, and see how confident the prediction is, right? If the network is not confident, which indicating the network, the input may be more challenging. So you have to go to the upper level, right? More higher resolution and using more layers to make a prediction. So they can build many levels of this kind of hierarchical, right? So always starting from the smallest, if the network is confident enough, this is one particular object, then we don't have to go with a deeper network to do the further processing, right? We can save some computation for this particular input. So in this way, overall, they are able to achieve, the computation, reduce the computational cost, okay? And this one, the MutualNet, actually is from my group and for my student, Yang. He also trying to propose these adaptive network. But here he trying to consider two factors. One is the input resolution, and the second is the network dimension, right? So during the training, the network can change, the width resolution, right? How many channels you want to use, right? So full network, let's say you have ResNet, and for the subnetwork, you can slimming the network, right? Maybe just take only maybe 80% or 70% of the channels for each of the layer to reduce the model size, right? You can come up with different ratios to have different subnetworks with different sizes. And the trade-off is between both, right? Not just considering the resolution only or considering the network size only. So we're actually considering the both, right? Is there the optimal combination, right? A smaller network, maybe this resolution combined with this network ratio, it can achieve the best accuracy and the latency trade-off. So that's the term, the mutual learning from resolution and the network configuration. And this paper here, the dynamic network quantization for efficient video inference is another dynamic words from the perspective of quantization, okay? And here is their main motivation or intuition, how to come up with kind of intelligent way to quantize each of the video frame to achieve computation efficiency, right? So for the normal network, right, it's gonna be operate on 30-bit, the full precision for each of the frame, right? We are doing frame feature encoding, and after all, we do the feature aggregation, then we can make a prediction, right? Which action this video belongs to, right? This is a long jump, right? So that's the traditional video action recognition, right? So you have a full precision for all the frames in this video, okay? So what they propose is that, can we using variable, bit width to encode different frames, right? Because not all frames, present the same important information, right? If you look at this long jump, right here, in the initial frame, right? Maybe this, athlete is just doing the running, right? Before the jump, right? And as you can think, this may not be informative, right? If I have another video which is running, I can have the same frame like this, right? So this actually is a confusing frame. Is this a running, or this is a jump, or maybe something else, right? Any of the, there's several actions, or sports activities can involving running, right? High jump, right? For example, not just long jump. So they want to intelligently, kind of assign different bit width to different frames. Only the full position will be assigned to the frame contain the most important or informative information, right? So this is actually the long jump, right? You can see the field with the sand, right? You have this kind of meters to measure, what's the distance, and this athlete is in this kind of position, right? This is a long, the jumping position, or just towards the landing, right? So this is the most important frame, right? For us, for human, to determine this is a long jump, probably we only need to look at this frame, right? Just as this single frame, then we can make a decision. This is a long jump, right? This is not a running or high jump or something else, right? And obviously, this is just after the jump, this athlete will go for some, media for the interview, right? Definitely this is irrelevant to this action, right? So they assign this skip, which is do not even consider this frame, just a 0 bit for this frame, right? We can totally ignore this frame because it does not contain any useful information to make a prediction this is a long jump, right? So that's their intuition or high-level ideas. So to achieve that, they train a policy network, Okay, so the policy network basically will determine, right, based on the features from each frame, how what's the bit width I want to assign to this frame, right? So we'll train this policy network. Basically, you can consider this is a classification, right? Let's say you have maybe 8 different bit levels, right? This is like 8-way classification, right? Which bit width I want to assign to this frame, right? Once this policy network is trained, then we can, make a prediction, right? Which quantization level we want to do to encode the feature of this frame. So this is able to achieve this kind of accuracy and computational latency trade-off. Okay. So based on this paper, I was trying to think, is it possible we can also design a dynamic networks for medical imaging? So I want you guys to think about this. Can we design a dynamic networks for medical imaging, right? So you can easily think something by taking some inspiration from here, right? Can we do something similar? Any ideas? Anyone?
Professor, can you repeat the question?
Yeah, so I was wondering, is it possible to design a dynamic networks for medical imaging as well, right? So since this seems to be a very promising idea to achieve some accuracy and the computation efficiency trade-off, right?
Mm-hmm. Professor, there is a possibility of doing that. Like, suppose the assignment that we are doing right now, there can be many misclassified images, or maybe the images which were not that much prominent, because that it's like a visual data set, but in real-time data sets and all, there can be some images where the MRI or the X-ray or something is not that prominent. Mm-hmm. And if we can like skip that, like, and assign no bits to it and just pass on to the next one, maybe we can develop something from that.
Yeah, right. So remember the first assignment, we are doing those kind of pneumonia classification, right? So these kind of resolution switch, adaptive resolution could be one solution we can apply there to gain some computation efficiency, right? So for some of the easy examples, maybe we only need a smaller network and the low resolution. So we can achieve some of the trade-off there. And also what I show you here is, we can take some of these quantization idea and apply to medical segmentation, right? So here I've given you this MRI, brain tumor segmentation, right? So if we, because we have like a multiple slides, right? So as you can see that, right, in the initial, maybe, because this is in 3D nature, right? So for some of the frames or slides, you can see that there is no tumor region, right? And also the foreground is actually very small, right? But when you implement, either any of the network, UNet or VNet, 3D UNet to do segmentation, you're using the same network, full precision to do the segmentation, right? But for this case, do we really have to consider the whole region, right? Because the foreground is very small. And do you really need to consider the full precision for this particular slice, right? Because it seems very homogeneous, right? A easier network may be also able to segment, this is a normal tissue, right? Only when you going larger, right? These foreground become larger, and also these tumor become to appear, right? There's some of the distinctions between these tumor tissue and the normal tissue, right? Maybe you need in a large capacity or using full precision to capture those small details, right? In order to distinguish, this is the normal tissue and this is the, abnormal, the tumor tissue, right? So, and even here, right, you have multiple different tumor types, then definitely the full precision will help. So this is just some ideas you can think about, right? In the future, if you are interested, to promote the computation efficiency for medical imaging. And these are some of the technique you can think about, especially, some of the dynamic networks, which is very interesting. Okay. Okay, so yeah, so that's all for the model efficiency, right? We talk about different ways you can achieve model efficiency, and we also touch upon a little bit on this kind of dynamics networks to also not just considering the characteristic of the network, but you also considering the features from your input, right? Is it going to be an easy, difficult samples to joint train a network that is able to trade off between accuracy and efficiency? Okay, so next we'll talk about something paper, related to paper presentation, because from next week, so you guys will, starting to present the paper in class. Okay, so I've already listed the schedule, so in the Canvas, so you can, based on your designated, date for your presentation, you can check that, right? When is the time for you to do the presentation? So I've listed here the paper title and the presenter. So make sure you prepare your slides ahead of time and practice your presentation. Okay. And before you, once the class you present your presentation, please submit the presentation slides. If you get, I will remind you, to submit that right after your presentation, because I want to put that in the course lecture just to let other people, they can go over your materials if they are interested to know more some of the details. And also, I will also grade the score of your presentation based on the content. Okay. So for the next week, March 1st, we have two presentations. One is the Beyond COVID-19 Diagnosis, and the second paper is the Big Self-Supervised Model Advanced Medical Image Classification. Okay, so that's March 1st, Tuesday. On Thursday, that's we have two other presentations. Data augmentation using learning transformation for one-shot medical image segmentation. And the second is also on the topic of medical image segmentation, but here it's similar to what we discussed today, right? Group shift pointwise convolution. I'm assuming this is targeting for efficiency. So I think it will be good to hear this presentation, how they achieve these kind of efficiency for volumetric segmentation. Okay. So the general guideline is, for each of presentation, roughly 20 minutes, right? So you have to, based on this time limit, prepare your slides, right? And your pace presenting the slides. And we follow that each presentation will have 15 minutes for Q&A and some discussion, right? So questions or to ask questions. And if there's anything we need to discuss further, so this is time for the Q&A and the discussion. So it's very important for everyone to participate in the discussion, right? To listen to the presentation and participate in the discussion. So I will also, there's like 5% of the total grades based on the participation, class participation discussion. So I will, monitoring that as well. So this is, I took from my first lecture just to give you, just keep reminding you, several important points to how to present the research paper, right? So just pretend no one reading the paper, but everyone should read the paper. Here, I'm just, when you present paper, just pretend no one read the paper. And you want to present the paper very clearly, right? The problem statement, the method, how they do the experiment, and what is the takeaway, okay? So I want to explain everything, the details very clearly. Okay, so this is just some of the guidelines you can think about to put in your presentation, right? So here are some of the details you can follow, okay? Especially, the problem statement, if it's very new or, unfamiliar topic, it will be helpful to spend more content or slides on introduce some of the background, right? Just to ease the audience to understand what is the problem, right? What kind of problems this paper trying to solve. Okay, so that means you may have to read other papers, right? Not just this paper you are presenting. You may have to read other relevant papers, which maybe this paper mentioned in the related work or in the introduction, to provide enough background knowledge to help people understand, right, the problem statement. Okay. And also, once you presenting some of the method details, right? What's their overall method, how each component works, and show the experiment. And you also want to, just like you're writing review report for the previous paper, right? So you want to kind of say what is the strength and weakness of the paper from your opinion, right? What do you think is the strength and weakness of the paper? So especially the weakness, so which we can discuss during the class, right? Other students can participate, right? After you reading the paper, what do you think? Maybe some other weakness the presenter doesn't mention. Okay, so those are the things we can discuss during the class. And also some maybe, what do you think about overall rating might be for this paper? And also even some of the future directions you can present, right? What do you think the direction is worth to investigate, or maybe even some of the improvement we can try, right? Okay. Okay, so here are just some of the guidelines. So if you want more, so you can listen to the first lecture recording and see I discuss all these details. Okay, but this is just like a general guideline to help you to prepare the presentation. Okay. Okay, so see, here are some of the resources I mentioned for mostly survey papers for quantization, knowledge distillation, and some of the existing code if you're interested in this field. Okay. Okay, all right, any questions?
Professor?
Yes.
Hi. So, is there any way you can have any host any office hours today or tomorrow?
I don't have time today, but yeah, can you send me do you just want to like a one-time request, or you want to in general have a Friday office hour? Because I do have office hour on Tuesday morning.
It was gonna take like a long time, so I guess like if it's fine with you, like maybe Friday.
Yeah, can you send me an email? Maybe we can have a like a one-on-one.
Sure.
Yeah.
Yeah, that should be fine.
Yeah, but in general, if you guys have any questions, right, maybe before your presentation, maybe a week before, right? Maybe then the week after you're gonna present your paper, and you still have some doubt about the paper you're gonna present, or you're not sure if your slides is good enough, you can always go to the office hours on Tuesday, 10 to 11. We can have some discussion in there. I can give you suggestions, to help you to improve. Okay.
Sure.
Okay. Awesome.
Thank you.
No problem. Okay. All right. If you guys don't have any question, we're gonna end here. Have a nice weekend, and I'll talk to you next week.
Professor, can I also join in that office hour on Friday?
Yes. So yeah, okay, also send me email so I can
All right.
maybe send you both. All right.
Okay.
All right. Cool. All right. Thank you, guys. We'll end here. All right. Bye.